All right, gang, Math 5130, going to be a lot going on in this video. You can probably tell that I've got StatCrunch up, I have R up, I already have a data set named body data loaded in R, and you can see that the sample size is 300. I've attached it, it's all good. Okay, so when I look at this, I see that if I'm running an ANOVA, I need a quantitative variable, which that serves as my dependent variable, and I need a categorical variable, which serves as my independent variable, but this needs to have more than 3 cases. So I noticed that I've got age 18 to 39 and sex female. Everything else out here is a potential for a dependent variable because it's quantitative. But the only 2 categorical variables I have are age and sex. So as I said before, when I go into R, I need to force all my categorical variables into being a categorical variable. We used to not have this problem with R, but we do now. So we just have to adjust and run these very, very simple commands. So now if I do table age, I can see that I have 113 participants ranging from ages 18 to 39. I have 127 ranging from 40 to 64. And I have 60 from 65 and older. I can also take a look at sex. Sex is just coded here. Male and female. Sometimes you get into female, male, non-binary, and different things. But whoever collected this data set and organized it made this decision. All right. So what's a potential research question? What I have chosen here is I've just chosen to examine if there's a statistically significant difference in mean pulse rate. So pulse rate is right there over age. Again, if I wanted to look at pulse rate, the mean of pulse rate over sex, and I'd use an independent samples t-test. But we are demonstrating an ANOVA here. So in this case, the dependent variable will be pulse. My independent variable will be age. And the null hypothesis, let me squeeze this in here, is that the mean for 18 to 39 is the same as the mean from 40 to 64. And it's the same thing for the mean of 65 and older. So this is the null hypothesis. The alternative hypothesis is at least one pair of means is statistically significant and different. So in ANOVA, in R, to run an ANOVA is really, really simple. We just want to call the command something, and I just call it our model. You could call it your ANOVA, whatever you want to call it, but I just call it model because it's kind of generic. And to run an ANOVA, we just run the AOV command. And the first thing we do is we put our dependent variable, which in this would be pulse, over the independent variable, which is the categorical variable with 3 or more levels. All right. From there, we just do summary of our model, and we get our ANOVA model. Now, first thing we get is we get our sum of squares for the treatment, and here we get our sum of squares for the error. Our model is statistically significant at the 0.05 level, and all of this information right here is reported like that. So F, because we're using the F distribution, 2, 27, because the first degree of freedom is 2, 27, 297, 2, 297. The second degree of freedom is 297, so that's reported as 2, 297. The F value, test statistic, rounded to 2 places, is 3.90. And our p-value is statistically significant at 1 asterisk, which we can see down here is the 0.05 level. So our model is statistically significant, and so we will definitely need to run a post-hoc analysis to see where the differences lie. So the next thing I would need to do is I'd need to report an effect size. Now, for us, for ANOVA, we'll report the effect size called eta squared. And eta squared actually looks like an N. It's like a cursive N. So this stands for eta squared. And the targets for interpreting eta squared, if we have something close to 0.01, we have a small effect. 0.06 is a medium effect, and 0.14 is a large effect. Now we can find the effect size a couple of different ways. We can just calculate it, and it turns out that the eta squared is equal to the sum of squares for the treatment or the group divided by the sum of squares for the error. And actually, the R has this as the sum of squares for the residual. So if I want to calculate the effect size, I can take the sum of squares for the treatment, which in this case will be the sum of squares for age, 1124, divided by the sum of squares. Ooh, that's wrong. That's wrong. Ooh, stop that. That's horrible. Can't believe I did that. Daggone it. All right, sometimes I get on autopilot and it doesn't work. Correction, correction, correction. This should be eta squared for the total, not the residuals. So in this squared eta, in this situation, eta squared will be calculated by taking 1124 divided by the sum of 1124 plus the 42856. So the total sum of squares is the addition of the two sum of squares that were given right here. So our eta squared is equal to 0.026, which I've reported right here. That value is closer to 0.01 than it is in the other standards. So we would report a small effect size. Even though we have a statistically significant result, the effect of the difference is very small. Now, R actually has, if you want to install a package, it's called an LSR package. It's kind of cool. It runs the eta squared for you directly. So any of these you could choose, the crayon mirrors, but we'll just come to USA, Ohio. Takes a little bit of time. Once I install it, as we talked about in a previous video, we have to access the library. And then the command is just eta squared. Everything is lowercase except for the S, which is a capital S. And then I just run eta squared on my model. So it's kind of a cool command because it will give me the effect size for all. If I'm running like a more than a one-way ANOVA, maybe I'm running a two-way ANOVA or three-way ANOVA, it will give me an effect size for all of the independent variables. In this case, we just have one, so it's kind of redundant. But you can see that the eta squared is the same as what we calculated by hand when I did it correctly, not had that goofy bozo moment that I did. So where are we? We have statistical significance, so we need to run a post hoc analysis. Now, there are different ways to run post hoc. The two I'm going to demonstrate to you are Bonferroni and Tukey HSD. Tukey HSD stands for Tukey highly significant differences. That's my preference. That's what I always report. And it turns out that it is super easy to find. Just run Tukey HSD and then run it on our model. Again, this is the model we created way back here. Whatever we called our ANOVA model, that's what we run our Tukey HSD on. And what it does is it gives us pairwise comparisons, and it gives us an adjusted p-value. So the p-values that are statistically, well, there's only one that's statistically significant, and that's when comparing the 40 to 64 with the 18 to 39. So what I like about this is it gives us our 95% confidence interval for each of these. Notice this one contains 0. This one contains 0, so we do not have statistical significance. And notice that this one does not contain 0, hence we have statistical significance at the 0.05 level. Now, these calculations take in a lot of stuff that's in consideration of making these calculations. Oh, let me show you one more thing. You can run what's called a pairwise t-test and run it over your pulse and your age, and then the p-adjust. If we want to run a Bonferroni, I believe that's the way we do it. I should have written this down. Yeah, that's it. Okay, so what it's doing here, it does a pairwise comparison as well. But notice how the p-value is 0.042 compared to 0.037. So again, as I said earlier, the Tukey is a little more aggressive. The p-value calculation is a little more aggressive. It'll result in a lower p-value. But in this case, there's no real difference. Again, I always will report the Tukey HSD, but I kind of want this on your radar because it's, a lot of times in health sciences, we need a more conservative comparison. Now, be prepared to have your mind blown here, because this won't make much sense to you on the surface. If I look at the sample means, so let's look at t-apply, so let's run pulse over age and run the means. Well, we have a statistically significant result for 40 to 64 and 18 to 30. So comparing 74, the mean, to the mean of 70.4, we have statistical significance. That difference is too much to conclude that the population means are equal under the calculation conditions. However, when we compare this mean to this mean, the difference is even larger, as we can see right here, negative 3.8 compared to negative 4.2. But the larger difference isn't statistically significant. Now, that kind of defies common sense or statistical sense, but what happens there in the calculation behind the scenes, if we look at the sample size of each of these, we can see that we have only 60 subjects in the 65 and older. So this group right here, the 65 and older, only 60, has less statistical power, so it's going to result in a little bit higher p-value. So it takes in a lot of considerations there. It takes in the variance, the standard deviation, and the sample size to make these really complex calculations. The beauty for you as someone who is just using statistics to make decisions and statements about relationships in your discipline, you don't have to worry about that. You just need to report that. All right? I think that's all I want to do in R. Let's run over to StatCrunch and you'll see how to run this in StatCrunch. So let's go grab our data from my computer. I think I called it body data. Yeah, there it is right there. And you'll have all this stuff. All right. All right, so to run an ANOVA in StatCrunch, super easy. I think most of you are really going to prefer this over R. Just go to ANOVA and go to one way. Now, we need values in a single column. We need to click this, and we want to run pulse over our factors, which is age. We want to compute the 95% confidence intervals using the Tukey HSD. We might as well just go ahead and run the equal variance test, Levine's. I'm not going to really reference it much in this video. Following video, we're going to actually write up, look at an example of presenting the results of an ANOVA, going through testing assumptions and reporting descriptives and all that stuff. But for right now, let's just kind of get our feet wet a little bit. So hit compute. Again, you got a lot of stuff there that can be overwhelming. You just have to break it down. I don't really care much. Well, no, I'm sorry. The first box up here gives us our descriptive statistics. So we can see the means across each group. We can see the standard deviations, and we can see the standard errors. You can see the standard error for 65 and older is a lot higher. That's what led to a lower p-value. But anyway, we get into our ANOVA, degrees of freedom 297, just as we had before. Test statistic 3.9, just as we had before. And our p-value statistically significant at 0.05, just as we did before. Equal variance assumption, not statistically significant, so there's no concern about that. We'll get into that more later in the write-up. But since we have a statistically significant result for our ANOVA, we have to go to a post hoc. And you can see that the p-value for the comparison of 18 to 39 to 40 to 64, as we saw in R, is statistically significant. Again, it gives the confidence intervals. For 18 to 39 compared to 65 and older, we do not have statistical significance, and we don't have statistical significance when we compare 40 to 64 to 65 and older. Again, you know, I just prefer R. I know most of you will not. Most of you would prefer the simplicity of drop and drag and, you know, that with StatCrunch, and that's cool. SPSS works very similar to this. All right, gang, I guess that's all I want to do in this video. I can't think of anything else. So the next video we'll write up this result, comparing the difference in mean pulse rates across age group, and integrate the effect size and look at descriptives and stuff of that nature. All right, take care.